Hello there, geometry students. This is Miss Graham, and today we are going to be learning about function composition. If you go to our class calendar, you can pull up the notes for today. There's a link on there that says function composition notes. You should also be able to grab a paper copy from the guest teacher. Our learning targets for today are we're going to write functions that describe the relationship between two quantities, and we're going to explore the composition of two functions through real-world scenarios. We're also going to learn what that word composition means. Let's go ahead and look at the story problem below. Hannah's housekeeping charges a $20 flat fee plus $12 an hour to clean a house. Number 1 is asking us to write a function C of H for the cost to clean a house for H hours. Instead of using f of x and x as our output and input, we're switching it up. So since we're using the variable h in terms of our input, let's figure out with the given information how we would write that part first. So we can see that it is a $20 flat fee, a one-time $20 fee. So I can write that as $20. And then I'm adding on $12 times h number of hours. So that would be 12h. Again, all of this is going to represent our output, so we can set it equal to C of H. Now, we've created functions like this before, but now we're going to continue to apply this idea of looking at the units and what it means. So number 2 is asking for what are the units of the domain and range of this function. Maybe let's review the idea of domain and range again. So remember, domain is going to be looking at our inputs. So we want to figure out what we're talking about. What comes first in this story problem? What is the thing we don't know? Technically, what does H represent? So H represents the number of hours. So for me, I kind of like to write it right above the domain. So that specifies it a little bit. For our range, that's our output. So think about the number of hours is going to output what? Well, it's going to output the money that Hannah makes. Now, in regards to domain and range, we have to think about what are all the possible values of hours, and what are all the possible values of the money that could be made. So for the domain, think about the number of hours worked. What is the lowest number you could possibly have? It's not just 1. You could have 0 hours. So we're going to start off by writing down 0 and think about it. We can continue to work more and more hours. It doesn't just necessarily have to be whole numbers. We could work an hour and a half, an hour and 45 minutes. So we're going all the way from 0 to infinity. So I'm going to be putting it in this notation where we're going to have a bracket on the end to include the 0 and a parentheses because we can't really include infinity. It just means the numbers keep going on forever. As for our range, that's a little bit harder to think about. We have to see what is that baseline that Hannah is going to be making, no matter even if she works 0 hours. Well, going back to the problem above, what we know is that she's going to make $20 no matter what. That's that one-time flat fee that she charges, even if it's for under an hour. So we know we are starting off making $20. If we continue to think about all the different types of hours we could input, you're probably thinking, well, we're adding multiples of 12. But remember, these don't have to be whole number of hours. We could have a half an hour. We could have 15 minutes, a quarter of an hour. So when we're looking at what is the possible amount of money made, it's actually also going to be just like our domain. It's going to go from 20 to infinity. Just like before, we're going to have a bracket on the end of 20 because that includes the 20. And the infinity sign, we're going to have a parenthesis on the end because we can't necessarily have infinity dollars made. Let's go on to look at number 3. It actually goes back and relates to that initial information that we talked about. So number 3 says, what is the slope of this function? So think all the way back to your Algebra 1 class, maybe 2 years ago. You're thinking back to what number is being times by our input h. And you can see we are looking at 12 as being times by h hours. And we can see it's the coefficient in our equation right there. So when we write down the slope, we can write down 12. Now, thinking back to our Algebra 1 class, a lot of the times for our slope, we saw it as a fraction. And right now you're probably thinking, what? It doesn't look like a fraction, it's just the number 12. Think about how I could put that 12 over 1. The reason I am comparing these two numbers together is we have an input and an output, right? We have some type of x and some type of y. Think back to slope. Slope stands for the change in y over the change in x. We're comparing the 12 to the number 1, and we're going to say what that actually means. That's what it means by interpret the slope as a rate of change. What does the number 12 mean in the problem, and what does the 1 mean? Well, for us, we know 12 is how much Hannah makes. So we can say Hannah makes $12, but how often does she make the $12? Well, that's where it goes back to for that 1. That's talking about hours. So the 12 goes to money, whereas the 1 goes to hours. So Hannah makes $12 per 1 hour worked. Whoa, I bet that was a throwback, huh? Cool. All right. Well, let's keep going with some more information about Hannah's housekeeping. So building off of this, Hannah can clean one room every half hour. So now it wants us to write a function for the hours needed to clean our rooms. So let's just use this baseline information. We'll come back up and talk about what we said for 1 through 3, but let's just look at what we know from this statement above here. If we're writing a function h of r, right, we know that's going to be our output. So h of r is our output, but what is our input? Well, we're looking at the information that we clean one room every half hour, and we're needing to clean our rooms. So think about how I can write a half hour, maybe as a decimal or as a fraction. Well, that's going to be a 0.5, or I could say as 1/2. Either way, you're timesing that by r, which is the number of rooms. So we can put 0.5r, or if you like fractions, you can put 1/2 r. I will probably be sticking with the first equation, but either one should work. Now here's the messy part. This is where the previous problem comes into play. This is our new notation that we're looking at. This is the new piece. So if you look below, it wants us to write a function. Whoa, how do I even say that? Well, we first start off looking at what's on the outside and reading it to the inside. So I have c of h of r. What I'm really looking at is I have this function c of h from previously, right? I have that from above, c of h. And I'm looking to put basically what I wrote in for h of r inside there. That's kind of the notation we're looking for here. Now, sometimes it's a lot easier to visually show it than explain it. So let's just write down our functions again. I'm going to write them down off to the side here. So number 1, c of h, when we wrote that down, was 20 plus 12h. And right above, we had h of r. That was equal to 0.5r. So what we're hoping to do is put in this function, h of r, in all the spots that I see h. Right there. I know, it's kind of tricky. This idea is going to be going in for h. Right on up there. So I'm going to erase this part right here just a little bit so that way you can see what we're working with. So when I write this down, I'm hoping that I can have C of H of R in the end. So again, I'm writing down the 20 plus 12H, but instead of H, I'm inserting 0.5R. So looking at this, we can multiply those two numbers. So that way, I end up with C of H of R equals 20 plus 6R. That's what I'm looking for my answer, right there. This idea that we just applied, where we inserted a function into the variable's input of another function, that's called function composition. That's what today's notes are all about. So now we're thinking, well, why did we do this in the first place? That's what we're talking about in number 6. It's asking us to take this idea and put 12 in for our variable, which is R in this case, and to verify, okay, what does that mean? What was the purpose of doing that? So let's take that function we just wrote and now put in 12. So I have 20 plus 6 plus 12. I can do 20 plus, well, 6 times 12 is 72. So I get 92. So remember, you want to bring down whatever that output label is. So I have C of H of 12 equals 92. And we're thinking, okay, what does this mean in terms of our problem? Well, remember, we're looking at a specific number of rooms and how much Hannah makes to clean the rooms. So if Hannah cleans 12 rooms, she makes $92. So that's going to be our statement that we're writing on down. Awesome. So we're going to say, if Hannah cleans 12 rooms, she makes $92. So all in all, we insert one function's output into the input of another function. And that's what it's asking us to say on number 7. Explain how the composition of functions forms a new function from the old/original functions. So you insert one function's output into the input of another function. Now, how do we know which output and which input to use? That's what we're going to explore more with some practice problems on the next page. So, looking above, we have 3 different equations that we're going to be working with. So I'm going to use some different colors to make sure I'm distinguishing them from each other. So I'm going to use red to symbolize f of x. I'm then going to use yellow to represent g of x. And last but not least, I'm going to use blue to represent h of x. Now, before we even start working with these 3 functions, I want you to write at the top of the page this new notation that we just learned. So we saw that we had a function, let's call it b of x, and we could insert it for the input of another function. Let's say a of x. So I can rewrite it as a of b of x. So b of x is going to be that output that I'm putting in for function a of x. What we're really showing here, and this is kind of a new notation, is we're taking function a and we're inserting function b into its spot. And we're keeping everything in terms of x. So this is another way that we can visualize and show this. You're going to see, wait a minute, we wrote an open circle. Isn't that multiplying? No, it's not multiplying. When we multiply, we have a closed or filled in circle just like that, but we're not doing that. It's an open circle. So that represents composition. So that's what I'm going to make a note of. That represents composition, meaning we're inserting one function into another. So both of these mean the exact same thing. Exact same thing. So let's go ahead and look at number 10 for starters. I know we're kind of going to jump around a little bit, but I think that's going to make it a little bit easier when we have problems build off of each other. So looking at number 10 for starters, we see we have this function g. And we see we have f of x. What I'm hoping to do is I want to rewrite g of x, but instead of x, I'm substituting the output of f of x into there. I know, it's kind of tricky, right? So let's write down what we have. So we have g of x, which instead of x, we're using f of x, right? We're inserting it in there, okay? So when I rewrite this, I'm hoping to have, instead of x's, I'm going to put x squareds wherever the x's are. So here we go. We're going to write this down. So I have 2x minus 1 as my function for g. And remember, instead of x, we're going to put an f of x into the spot of x. F of x is x squared. So I insert that in there. And that is my new function. If we go back up to number 8, it builds off of what we just did in number 10. It takes the same idea where we're inserting f of x into g of x, but now it added a new piece. Oh, okay. We're now taking that new function and inserting a number 2 into there. I know, right? That's kind of crazy. So looking at that 2, we're taking what we just wrote from before. So I'm going to write that down again. 2x minus 2. Sorry, 2x squared minus 1. And then instead of x, remember, I'm inserting 2. Ooh, okay. So I put a 2 into the spot of x. And then I evaluate this function. So I have to square first, since that follows the rule of PEMDAS. So I have 2 times 4 minus 1. 2 times 4 is going to be 8. So I have 8 minus 1. 8 minus 1 is going to be 7. So looking at this, I have g of f of 2 that equals 7. Let's try another problem. Let's try 13. And in fact, I want you to try that one on your own. So go ahead, pause the video here. I want you to try 13. Again, it's actually just like number 10, just showing a different notation. It doesn't say H-O-F, it says H of F. So see what you can do. Think of which part you're inserting into the other. All right, did you get the following? Did you get 4x squared minus 3? Awesome. Remember, all we're doing is we're inserting x squared into the spot of x. Let's try one more on our own for good measure. Let's go ahead and try number 15. So go ahead and pause the video and try number 15 right now. All right, did anyone see that number 15 is just like number 10, just showing a different way to write? We're inserting f into g. Yeah, so we can actually take exactly what I wrote before from number 10, And now insert 1 into that spot. So I know some of my work went a little bit long, so I apologize for that. But don't forget, in the end, you really want to make sure you're bringing down g of f of 1 for your final answer. Again, I know I ran out of a little bit of space, so I'm just going to erase a little bit here so that way I can bring my work into play. All right, so remember I had 2 minus 1, so lo and behold, I ended up getting 1, and this is my resulting function. I can see that when I inserted the input of 1, I got an output of 1, ironically. And now I'm going to go ahead and take it up a step further. If we go back up to number 11, we're going to see that it's not just as easy as inputting x or x squared into a spot. We might have to use the distributive property to help out with some of the work. So up here, we can see we're inserting, mixed up my colors, we're inserting h of x into g of x. So when I write this down, my function g of x is 2x minus 1. So 2x minus 1. And instead of having x there, I have to now put, oops, that was a little too big to erase. I now have to put whatever I get for h of x. Well, I really have to squeeze it in there, huh? I'm looking to insert, what was that? 4x minus 3. Oh, okay, so 4x. I'm going to erase this a little bit, just a smidge. All right, there we go. So I have 4x minus 3 in the spot of x. And don't forget, we still have the other original functions. I still have minus 1. Now, looking at this, you can see we have the distributive property. We're going to have to multiply 2 times each term inside. So that way I get 8x minus 6 minus 1, and I can combine like terms, the negative 6 and the negative 1. So I get 8x minus 7, and lo and behold, that's what I get when I have g of h of x. Whoa, so we got number 11 done. Let's jump down to number 16. So 16, another step up. And it's going to throw back to Algebra 1 class. So hopefully you're having good memories of your Algebra 1 teacher. Right now, we're hoping to insert h into the function of f. So let's remind ourselves what f was again. F was x squared. But now, instead of writing the x, I have to insert whatever my h function is, which is 4x, and again, I ran out of a little bit of space. I'm going to squeeze that in there. So I have 4x minus 3, and that's what's getting squared. Whoa. You're probably looking at this, and a lot of you are probably thinking, ooh, I just distribute the squared, right? No, be careful. Don't do that. That's actually a big no-no. Think back to what the exponent means. It's different when we have a number out front and we're distributing that. The exponent means we have 2 of something that we're multiplying, right? Something times itself. So really what I'm saying is I have 4x minus 3 times itself. So times 4x minus 3. You will get a very different answer if you try to distribute. You're actually going to lose an entire term. Looking at this, now I can apply the distributive property. That's what I learned earlier this week. All right, we're going to test your knowledge. Pause the video, see if you can use the distributive property to come up with your 3 terms. All right, check your work with mine. Did you end up getting 16x squared minus 24x plus 9? That's what's equal to f of h of x. Now, what I'm going to say is the rest of the problems that we didn't get to. So looking at numbers 9, 12, 14, and 17, those are actually going to be optional. We did enough practice of a couple of examples, even some tougher ones, right, which involved the distributive property. But if you want to go through and practice those on your own, I do have the answer key to the notes posted, so you could always check your work. Otherwise, you can go on to tonight's homework, which is the function compositions worksheet. All right, happy mathing.